So, we will be continuing with our discussions on the separated flow model as we were doing. So, till the last class whatever we have done, we have first taken up the two fluid model and then we had derived the continuity and the momentum equation for phase 1, for phase 2, and after that what we try to do is we try to find out what happens when there is mass transfer between the phases, what happens when there is some change of phase, maybe some sort of boiling, condensation, whatever it is. So, under that condition what happens? What I forgot to take derive was, and then after that what we did, we derived the mixture the momentum equation for phase 1, momentum equation for phase 2, and then we combined both of them in different ways. One gave us the relative motion equation, the other gave us an expression of the pressure gradient. So, today what we are going to do is we will try to express the pressure gradient equation, the mixture pressure gradient equation in terms of known input parameters as much as possible. We will see that we can substitute all the terms. If we look at the mixture pressure gradient equation, we find that I will just write it down once more. I do not know whether it is there or not with me. Anyhow, I will just write it down. If you just notice the mixture pressure gradient equation, it was something of this sort, 1 minus alpha rho 1. This already you have it with you, because in the last class itself I had discussed this part, tau W 1 S 1 by A plus tau W 2 S 2 by A plus 1 by A d d z of W 1 U 1 plus W 2 U 2. So, this was all that we had. Okay. So, therefore, we find that in this particular case more or less alpha is also an unknown here. Why? Because unlike homogeneous flow model, we cannot assume that alpha equals to beta. So, alpha is the in situ volumetric composition. When it is the in situ volumetric composition, it is not within the control of the experimenter or the designer. As I have already mentioned, it depends on a number of input parameters, but the dependence is not very straightforward. So, therefore, it has to be determined or estimated either experimentally or theoretically from some known input parameters. So, this is also not very straightforward. Other than that, this particular frictional pressure gradient, of course, we have to discuss methods, and here we find W 1, W 2 are known, but U 1, U 2 are not known. Again, they are the in situ velocities of phase 1 and 2. Okay, and they vary just because this in situ velocities, they are functions of specific volume, they are function of pressure gradient and so on and so forth. So, we have to express U 1, U 2 in terms of known measurable parameters, or in other words we have to express the acceleration pressure gradient in terms of known input parameters, and once we can do it, then probably we can find out the pressure gradient or the pressure drop across a known length, provided we have some idea of how to estimate the frictional pressure gradient. Okay. So, today what we are going to do is we would try to do the pressure drop calculation from known input parameters, but before that yesterday I had forgotten to mention the, or rather I did not have time to mention the mixture energy equation. In the same way you can derive the mixture energy equation. I am just writing the final form. The derivation is left as an exercise or as a home assignment for you. This was the mixture momentum equation, which we obtained by adding up, if you remember, by adding the equations we had derived for the momentum balance of phase 1 and phase 2. We had just added them up and obtained this particular equation. In the similar way, we can find out the energy balance equation, and for unit mass of the fluid 1 by W T P, it will be something of dq, the heat flux dz, minus dw, the work done, which is usually equal to 0, and this is equal to ddz of x h 2 plus 1 minus x h 1, or in other words this is nothing but the two phase enthalpy plus the two phase kinetic energy for unit mass of the fluid, unit mass of the mixture, in other words u 1 square by 2 plus g sin theta. So, this gives us the mixture energy equation. Again from the first law you can find out, first law for open systems, this particular equation can be easily derived. Okay. Well, now we go to discussing the pressure drop calculations. Pressure drop calculations from known input parameters. So, in this particular case, if you notice here, so we will be substituting your u1 and u2 from here. So, we will consider the acceleration pressure gradient. Okay. Acceleration pressure gradient, it is nothing but 1 by A. I would request you to do the derivations yourself and then compare with my derivations, otherwise it is going to be very dry, and finally, when you just see the derivation, note it down, and when you go to your hostels, it is very difficult for you to derive the whole thing together, because lot of things have to be substituted. So, the best is if you listen to my instruction, do the derivation on your own and then compare with the final form I have got. Okay, that will be the best. So, in this particular case, we find that we know from mass balance W1 equals to, just from the basic equations I have started. So, from mass balance we know this, okay, or in other words this is equals to rho 1 u1 a into 1 minus alpha. In your exams, if you are supposed to do any derivation, start from the basics and then start deriving, okay, otherwise it is going to be very difficult. Or we can find out W1 by A, this is equal to G1, agreed, and this is equals to rho 1 u1 into 1 minus alpha. This G1, this is nothing but G into 1 minus x, which is equal to rho 1 u1 into 1 minus alpha. So, from here we can find out u1 in terms of measurable properties or in terms of alpha. Alpha, see alpha, already you have this alpha variable in your mixture momentum equation. So, one, if you can reduce the number of variables, that is our target, isn't it? So, therefore, we get u1 in terms of alpha as well as other known measurable properties. So, u1 it becomes g into 1 minus x by rho 1 into 1 minus alpha. G we already know it is nothing but G1 plus G2, isn't it? Or in other words, it is nothing but W1 plus W2 by A, isn't it? So, x we can obtain from heat balance equation or energy balance, rather it should be, we can get it from energy balance equation. So, this is also an input, okay, from heat balance. Rho 1 we can find out from standard tables and or in other words, if it varies with pressure, we can find out how it varies with pressure either from thermodynamic equation of state, usually that happens for the gas phase, rho 2, rho 1 is usually constant. Okay. In case it varies, we can find out the variation either from the thermodynamic equation of state, or maybe when there is some phase change we can consider that. Okay. And therefore, u1 it is obtained in terms of measurable parameters. Similarly, u2, proceeding similarly, we can get it as ux by rho 2 alpha. Okay. Now, if we substitute these two here, then in that case what do we, if we substitute u1 and u2, okay, just see. So, for u1 we get g into 1 minus x by rho 1 into 1 minus alpha, isn't it? W1 by A, that is also g into 1 minus x, isn't it? So, what we can do is this W1 it can be written down as g into 1 minus x, correct. This can be written down as g into x, very sorry, w into 1 minus, w into x, agreed, yes or no? If that can be done, this w can be taken out, okay, and we can get w by A, which is nothing but g, fine. So, let us do this and see what we get. So, minus dp dz acceleration, this is equal to, we have 1 by A, we have taken out the w. So, it becomes d dz of 1 minus x u1 plus x u2, is not it, where this w by a, this is nothing but g. Okay. Now, in this equation, if u1 and u2 are substituted from these two equations, okay, u1 from this particular equation, this is g into 1 minus x by rho 1 into 1 minus alpha, and u2 equals to g x by rho 2 alpha. If these are substituted, then what do we get? Another g comes out from here and it makes a g square outside. Okay. So, therefore, from here we get g square d dz 1 minus x into the 1 minus x here. So, it becomes 1 minus x whole square by rho 1 into 1 minus alpha plus x square by rho 2 alpha, is not it? Now, in this particular case, we find that what are the things which vary with z? X varies with z if there is some heat flux. If there is no heat transfer, no heat, it is under adiabatic condition, x does not vary. Since we are dealing with the most generalized case, we would like x to vary, and if the problem you have to apply for an adiabatic case, then in that case you can assume that x is a constant. In that case, you do not assume x to vary, correct. Rho 1 usually it does not vary, but we will just keep it as dV1 dP or something, and then we will eliminate it for as the case. Alpha definitely varies with z. If x varies, then also alpha varies. If x does not vary, then also alpha can vary. Okay. So, therefore, we find that all these terms they vary with z. So, therefore, if we have to find out this, in other words, can be written as g square d dz of 1 minus x whole square by rho 1 into 1 minus alpha plus d dz of x square by rho 2 alpha. We can write it down in this particular way. So, therefore, let us see this d dz of, say, let us take up this term first, x square by rho 2 alpha. This is no fluid mechanics, no multiphase flow, this is basically differentiation, but very long differentiations which will give you very long equations, and you might get confused and you might make a lot of careless mistakes. So, that is the thing which you have to look out for when you are doing particularly this derivation. These are naturally they will be the most complex derivation as far as multiphase flow is concerned, and I would request that you would practice those derivations quite a number of times, otherwise you will not get yourself familiarized with these particular things. Okay. So, therefore, this is nothing but simply the differentiation I am doing d dz of x square, okay, x is the quality, plus x square by rho 2 1 by alpha plus x square by alpha d dz of u2 sorry v2, rho 2 I have made it v2. Agreed? Any problems? So, therefore, simply whatever you have learned in your class 11-12, nothing more than that, 2x dx dz. I am, see, the thing is, the final expressions you will find in several textbooks, but the total derivation you won't find, and usually students they have a problem. It is just have to sit and do, there is nothing very great in it, but usually students they have a problem in deriving the whole thing. So, therefore, I will do the whole derivation. I do not even have slides because they might become very dry, means it will be difficult for you just to see a large number of equations without derivation. So, I am doing the derivation in the class, so that you can actually follow the stepwise things and you can actually arrive at the final expression from the basics. So, just to avoid any sort of confusion from your side. Okay. So, therefore, this becomes 2x this plus it becomes x square by alpha, if I do this part first, dv2 dz, and please look out whether I am making any mistakes or not, that can also happen, minus for this term if you do, it is going to be minus x square v2 by alpha square d alpha dz. Just see whether all of these terms are correct or not. Okay. First term on differentiating gives you 2x dx dz with a 1 by rho 2 alpha. The second term naturally it gives you minus 1 by alpha square d alpha dz, and there is an x square by rho 2 or x square v2 here. okay, and this one definitely gives you x square by alpha dv2 dz or ddz of 1 by rho 2 in whatever way you want to write it. Okay. So, now from here what do we get? From here we get this is nothing but 2x v2 alpha 2, or in other words if we just transform everything into v2, then in that case this simply gives you 2x v2 by alpha dx dz plus x square by alpha dv2 dz minus x square v2 by alpha square d alpha dz. Fine, just the thing which I had derived. Agreed? This is equal to, I should write d dz of x square by rho 2 alpha. Fine. So, this was one particular term in the acceleration pressure gradient. Same way we can do for the other term as well. Okay. Just you have to keep in mind that here it is 1 minus x square. So, therefore, it will be minus 2x etcetera etcetera. So, certain things you have to keep in mind. So, in a similar way if we perform the differentiation of d dz of 1 minus x square by rho 1 into 1 minus alpha, what do we get? We get v1 by 1 minus alpha. Same way let us proceed so that you can understand it, or you can do the derivations yourself. dv1 dz plus 1 minus x whole square v1 d dz of 1 by 1 minus alpha. So, this if it is done, this gives you v1 by 1 minus alpha 2 into 1 minus x minus dx dz, isn't it, plus 1 minus x whole square by 1 minus alpha dv1 dz, and again plus 1 minus x whole square v1 d alpha dz. This gives you minus 1 by 1 minus alpha whole square into minus 1. Simply differentiation I have done. I am not jumping steps, because in case I also make some mistakes, we will not be able to find it out. Okay. So, therefore, from this particular term if you see it is basically d dz, or rather this term it can be written d d 1 by alpha 1 minus alpha of 1 by 1 minus alpha into d 1 minus alpha dz. Okay. So, d 1 minus alpha dz gives you minus 1, and the other part differentiation gives you this, right. So, these parts, these things please derive on your own and then you try to find it out. So, this gives you minus 2 into 1 minus x v1 by 1 minus alpha dx dz plus 1 minus x whole square by 1 minus alpha dv1 dz plus 1 minus x whole square v1 by 1 minus alpha square d alpha dz. Correct. So, therefore, one particular equation for x square by rho 2 alpha d dz of this I have found out. The second expression is for this part d dz of 1 minus x square rho 1 by 1 minus alpha. So, this is one particular expression, this is other. Now, once I substitute both these equations here, I get the final expression of acceleration pressure gradient in terms of known measurable parameters. It will just contain alpha extra, okay, and x, that also we consider to be a known measurable parameter. So, if we substitute this particular equation and this particular equation in the acceleration pressure gradient equation, the final expression which we get is something of this sort. It is minus, simply we substitute it, we get something of this sort. This is equal to g square 1 minus x whole square by 1 minus alpha dv1 dz plus x square by alpha dv2 dz plus 1 minus x, simply I am writing down whatever I have got so far, by 1 minus alpha whole square dv1 d alpha dz minus x square v2 by alpha square d alpha dz plus 2x v2 by alpha dx dz minus 2 into 1 minus x v1 by 1 minus alpha. So, therefore, there are 2 dx dz terms, 2 d alpha dz terms and 1 dv1 dz and 1 dv2 dz. This is all. Okay. Now, here we find that why does v1 or v2 vary with z? Any idea why does v1, v2 vary with z? Just because pressure varies with z. They are a function of pressure. How to know in what way they vary with pressure? One is the PVT behavior of gases, or simply from the equation of state we can find it out, isn't it? Or suppose there is a change of phase, then in that case we can also find it from thermodynamic tables as well. Okay. So, we know that dv2 dz and dv1 dz, they are simply, these terms arise simply because v1 is a function of pressure, v2 is a function of pressure. Fine. So, if that is the case, then in that case dv1 dz, this can very well be written down as dv1 dp into dp dz. Yes or no? Same way dv2 dz, this can be written down as dv2 dp into dp dz. Agreed? For most of the situations we will find that this term is not there, this cancels out. Okay. Now, we are doing it keeping everything intact, but remember for most of the situations this term is going to cancel out. Depending upon the problem you will be given in the mid-sem or in your examination, you will eliminate them from the very beginning and you can start doing, no marks will be deducted. In fact, your derivation will be slightly simpler in that particular case. Okay. So, remember this thing. So, therefore, we find dv1 dz that arises or that can be substituted with dv1 dp dp dz. Similarly, this dv2 dz that can be substituted with dv2 dp dp dz. Fine. Now, you tell me why does alpha d alpha dz, from where does this come? See, dx dz's, they are inputs. It just depends upon the amount of heat flux. If we have a constant heat flux, there are situations where more or less dx dz is a constant, or in other words x varies linearly with z, such situations. So, we need not bother about dx dz terms, they are simply inputs. Okay. Now, d alpha dz, can you tell me why this d alpha dz term arises? On what does your void fraction alpha depend? Any idea under this situation, just like V1, V2, on what does your alpha depend? It depends upon, if there is a phase change, definitely it will depend upon pressure, x phase, if it is phase change, then it will depend upon x, plus it will depend upon pressure as well, because depending on the pressure the velocities etc. are going to change. So, alpha, just like V1 was a function of pressure only, V2 was a function of pressure only, we find alpha is a function of x as well as p. Agreed? So, therefore, d alpha dz that can be written down as del alpha del x at constant p dx dz. Again this becomes an input, okay, plus del alpha del p at constant x dp dz. This again depends on pressure. Okay. Now, we can substitute, instead of dv1 dz, we can substitute this particular term, instead of dv2 dz we can substitute this, and instead of d alpha dz we can substitute this particular term. Okay. That will give us the final acceleration pressure gradient. Is it clear to all of you? That will give us the final acceleration pressure gradient. Fine. You just substitute and find out the acceleration pressure gradient, and then for see finally what we want to do is we would like to express the pressure gradient here in terms of known measurable quantities. So, once you substitute these particular terms in acceleration pressure gradient, and then we can substitute this acceleration pressure gradient in the total pressure gradient expression, right. In that case what we do, when we substitute it in the total pressure gradient expression, we find that even on the right hand side we have some dp dz terms, is not it, which again we have to take to the left hand side. So, what you are required to do is you first substitute your these equations in your acceleration pressure gradient in order to get the final expression of the acceleration pressure gradient. And after that, this acceleration pressure gradient expression that has to be substituted in the total pressure gradient expression. Once this substitution is done, then what do we get? On substituting this particular way, we get minus dp dz. This is equal to the first term, if you see here, this is g sin theta into this whole thing 1 minus alpha rho 1 plus alpha rho 2, which is nothing but this term, this whole term, this is equal to rho Tp, is not it. So, therefore, we can write it down as rho Tp g sin theta plus the frictional part tau W1 S1 by A plus tau W2 S2 by A plus, if this acceleration pressure gradient is substituted, we get g square taking the dp dz terms together. Okay. What we do? We first, once we substitute this, we find that there is a g square, and then here instead of this dv1 dz, we can write it down as dv1 dp into dp dz. So, this becomes a dp dz term. Instead of this, we can write down dv2 dp into dp dz. This can also be written, and instead of this d alpha dz, I can write down this whole thing del alpha del x at constant p dx dz, and again another dp dz related term. Okay. So, therefore, 1, 2, 3 dp dz related terms we get from here. So, therefore, if we write them down, we find that this gives us 1 minus x. You just compare with the thing which you have got, one term associated with dv1 dp, then there is a second term associated with dv2 dp, and there is one more term which is associated with plus 1 minus x square v1 by 1 minus alpha square del alpha del p constant x minus x square v2 by alpha square del alpha del p at constant x. Agreed? Okay. This term I missed out. This term also gives you the same thing. Okay. So, therefore, 4 terms associated with dp dz, one term contains dv1 dp, other term contains dv2 dp, and the rest 2 terms they contain del alpha del p at constant x, right. And along with that, whatever the rest of the terms containing dx dz, and then all those terms are remaining. So, therefore, we get, sorry, this will be like this curly bracket, and then along with that what we get is plus 1 minus x whole square v1 by 1 minus alpha whole square minus x square v2 by alpha square del alpha del x at constant p dx dz, terms containing dx dz, and the term containing del alpha del x at constant p, plus we have 2x v2 by alpha minus 2. Please do this practice this derivations a number of times, or else it will simply be difficult for you. That is the only point. Okay. So, this is the entire total pressure gradient equation that we have gone. Okay. First term it is the gravitational pressure gradient, the frictional pressure gradient, and then a g squared term associated with dp dz. This entire portion will come to the left hand side, okay, and the remaining terms they contain dx dz. Just substitute and see whether you have got these terms or not. Okay. Now, once we get this, what we can do, we can simply bring all the dp dz containing terms to one side, so that it becomes easier for us. Okay. And if we do that, what do we get? We get minus dp dz into 1 plus g square 1 minus x whole square by 1 minus alpha plus x square by alpha dv2 dp plus 1 minus x square v1 by 1 minus alpha square del alpha del p at constant x minus x square v2 by alpha square del alpha del p at constant x. This whole thing, this is again equal to, sorry, rho T p g sin theta plus frictional component of it plus g square dx dz, because all the other terms they contain dx dz, 1 minus x whole square v1. Please do these derivations, otherwise it will be slightly difficult for you. Del alpha del x at constant p plus 2x v2 by alpha fine. This is the total pressure gradient expression that we have here. A huge expression which might frighten you, but if you do it slowly, if you try to do everything, understanding everything and do not make mistakes, then I do not think it is going to be very, very difficult for you. Okay. So, from here what we can do, you can just note down the derivations which I have made it in, that is going to be easy for you. It is simply dp dz into this whole thing, this is equal to this particular portion. The final expression definitely you will be getting in textbooks, but arriving at the final expression, that probably you have to do it on your own. So, all of you have copied down the expression, fine. So, from here what do we get? From here we get that the final expression of minus dp dz in terms of known measurable parameters, that is simply, just I bring the left hand side, the multiplicating factor of minus dp dz to the right hand side, simply nothing else. So, this is going to be rho T p g sin theta. Apparently, it is slightly boring, but definitely when we do problems we find that we deal with certain simpler situations, because certain things tend to be negligible under certain conditions. Then situation becomes easier, but you should always know the actual expression, so that you can know where and how the simplifications have to be done. Again the same thing I am just writing it down so that maybe if I have made a mistake or you have made a mistake in the previous expression, at least you can see and you can correct it here. Del alpha del x at constant p plus 2x v2 by alpha minus 2 into 1 minus x v1 by 1 minus alpha, this divided by 1 plus g square whatever was there. And if you remember in the homogeneous flow model as well, we had this dv2 dp and dv1 dp term there. In addition, these two terms we already had in the homogeneous flow model, isn't it? And then this denominator term we compared it with the compressible flow situation, and then we said that in the compressible flow situation it corresponds to 1 minus ma square, where ma is the Mach number, which is nothing but the ratio of the velocity of flow to the velocity of sound under the same conditions of temperature and pressure as that of the flow, isn't it? So, therefore, we find out that accordingly we had told that in the homogeneous flow model definitely this would correspond to the Mach number, or rather this would correspond to 1 minus ma square, okay? And 1 minus ma square, from here we can get the criteria for Mach number equal to 1, which is nothing but the condition of choked flow. So, therefore, in this particular case also, if I complete the denominator, in this particular case also, this denominator, it should correspond to 1 minus ma square, okay. This whole thing, it should correspond to 1 minus ma square, and therefore, this should correspond to the Mach number for two phase flow under separated flow situations. Okay. So, if this whole thing, this is equated to 1 minus ma square for two phase flow under separated flow conditions, then from there what are we supposed to get? We are supposed to arrive at some particular condition which will give us the condition of choked flow for two phase flow when the two phases are flowing under separated flow conditions. Is it clear to you? The logical thing which should have been was that, see, we should have started with the basic mixture, the basic equations for component 1 and component 2. Okay, we had written down the basic momentum equation. In that particular basic momentum equation, for what we should have done was, we should have written down, or we should have expressed it in terms of dp dz. Okay. That would have given us the condition of choking for phase 1, for phase 2. Okay. For the two different mixture momentum equations which were derived initially, if we apply in the same way, see there also we had dv1 dz, dv2 dz. Then in the same way, if we would have applied dv1 dp, dp dz, etc., then from there also we would have arrived at conditions of choking for phase 1 from the momentum balance equation of phase 1, isn't it? And for phase 2 from the momentum balance equation of phase 2. Okay. So, this would have given us the condition of choking for phase 1 and for phase 2, but we will do that in the next class, and then you will find that this will in no way guarantee us the condition of compound choking, because that in the next class what I plan to do is, first I will be deriving the condition of choking from this particular denominator, the denominator which I have written down here. Okay. If you see my the thing which I have written down in this particular in the written matter, then you will find that from this denominator which I have written down, equating this to 1 minus ma square, we will be getting a condition of choking. This condition of choking we are getting from mixture momentum equation. Okay. There we will find that there is some sort of anomaly in the expression, and that had arisen just because there were certain reasons. Since we had considered the mixture momentum equation, we did not consider the interaction between the phases. So, after that what we will do in the next class is, after that we will take up the two phases separately. Okay. The basic equations which I had written down, the momentum equation for phase 1, the momentum equation for phase 2. Okay. And then from each of the momentum equations, I would like to derive the condition of choking. That will give me the condition of choking for phase 1, condition of choking for phase 2. If I combine the two, I will find that there will be one del alpha del z or something term, which would show us that just ensuring that flow phase 1 is under choked flow, just ensuring phase 2 is under choked flow, it does not guarantee that the two phase mixture is under choked flow. Because what happens that whenever you have, for this two phase flow is occurring, the alpha is adjusting itself accordingly. So, therefore, just phase 1 being choked in choked flow, phase 2 being in choked flow will not guarantee that the two phase mixture is in choked flow. For that we have to consider the variation of alpha with z or the variation of alpha with p. Okay. So, initially we will be doing the condition of choking from mixture momentum equation, or in other words we will be considering the denominator which we have derived in this particular case. After that we will be considering the condition of choking by considering the two phases separately, and just to make a very generalized thing, we will be considering the component momentum equations which we had derived by considering change of phase as well. If there is no change of phase, simply the change of phase terms will be cancelling out, or in other words the terms containing eta. If you remember, in the last class we had derived there were some terms containing eta, where eta was the fraction of the force which arose due to change of phase. So, out of the total force that arose due to change of phase, we had ascribed eta fraction of the phase of the force to phase 2, 1 minus eta fraction of the force to phase 1. Okay. So, if you do not have a phase change, simply those particular terms containing eta will be cancelling out. Okay. So, just to avoid doing the derivation once for normal two phase flow under separated flow under adiabatic conditions, and then again considering change of phase, what we will be doing is, after we have considered the mixture momentum equation, we will be considering the we will be finding out the condition of choking by considering the separate equations of momentum for phase 1 and phase 2, keeping in mind that change of phase is also occurring. Naturally, this will give us to much more complicated equations, but this will be a generalized case. Did you get all of you? So, accordingly what we will be liking to do, we will be doing that, and naturally please come prepared, otherwise tomorrow's equations will be slightly more complex. Okay, I am not going to start it today just because you need to prepare the whole thing, so that, see, complex means basically we have to use the continuity equation and we have to use other equations and substitute them, so that we can arrive at an equation which can be expressed in terms of known measurable quantities as far as possible. Okay. So, this is the thing which we will be doing in the next class. Now, after that what we would like to do is that, if you see what we have done, basically our intention is simply to find out, or our intention is simply to predict the pressure drop for two phase flow under separated flow conditions. This is our intention. Okay. For that we had written down the momentum equations, and after writing down what we did, we combined them to find out the mixture momentum equation, and the final expression we have got is this particular whole equation, which enables us to calculate pressure gradient from known input parameters. If you go through this particular equation term by term, you find that most of the things you can obtain from input conditions as well. Okay. For example, x can be obtained from heat flux equation, V1, V2, these things you can get from standard conditions, etc., etc. The things which are unknowns in this particular equation, first thing is your frictional pressure gradient. Now, this had also created a problem in our homogeneous flow model. if you remember, there also we did not know how to express the frictional pressure gradient. Why it becomes a problem? Because how the fluid will interact with the wall, that depends upon the nature of the fluid, that depends upon the composition of the fluids, if it is a two fluid or if it is a multi-phase mixture. Okay. So, therefore, under that condition, under homogeneous flow condition, the situation was simpler. Why it was simpler? Because we had considered that the two phases were intimately mixed, and when they are intimately mixed, what happens? They flow as a pseudo fluid. So, therefore, we assumed that, well, this is a single fluid which is flowing, a pseudo fluid which is flowing with suitable average properties, and this particular fluid as a whole is interacting with the wall, and accordingly the wall shear stress can be calculated. But under that circumstance also we found out that even if we use simply the single phase equations which are available, under that conditions also we found that we had to encounter certain unknowns. We had to resort to certain empirical correlations. Why? Because in single phase flow we found out, how do we find out frictional pressure gradient? We find out frictional pressure gradient in single phase flow from Moody's plot. Okay. In other words, we find out the frictional pressure gradient by using a friction factor definition, where this friction factor, it is a function of Reynolds number. Fine. Finding out Reynolds number for single phase flow, it is very easy, it is just based on measurable properties. It is nothing but Re equals to dG by mu. Okay. So, therefore, finding out friction factor, it is just friction factor for single phase flow, it is a function of Re, where Re equals to dG by mu. Okay. This G, or in other words, this is better written down as du rho by mu. Okay. There, see, there was no chance of u varying within the flow, there was nothing like in situ and input velocities, isn't it? This u was simply, you measure the volumetric flow rate, divide by the cross sectional area, you get u. D is the pipe diameter, rho and mu, these are simply fluid properties. So, therefore, this Reynolds number, it was an input there. Similarly, if we had considered the homogeneous flow model, the same way we could write dGTP by mu Tp. This I had discussed in the last class as well. This is FTP, this is a function of RETP, where this equals to RETP. But we found that even for such a simple case also, we found that finding out mu Tp is a challenge. Okay? Because for density we can very well say that, well, density, it is a function of the component densities as well as the void fractions or the volumetric proportion of the two phases inside the flow. And since it was a no slip condition, the volumetric proportion with which we had introduced the flow was equal to the volumetric proportion with which the two fluids were flowing inside the pipe. With what volumetric proportion we had introduced them into the flow, that is already known to us. What we cannot control is what will be the proportion inside the pipe. For homogeneous flow, they are the same. So, finding out rho was no problem. Okay? But finding out mu Tp, how this viscosity, the two phase viscosity, that varies with the composition, was not very well known to us. Okay? So, therefore, there also we faced a problem. Now, in this case also we find that the frictional pressure gradient, this is an additional problem. Basically, they can be written down as, this can be written down as something like FW1, which is the interaction of phase 1 with the wall. This can be written down as FW2, which is the interaction of phase 2 with the wall. So, therefore, to make matters simple, we can simply write the frictional pressure gradient as the summation of the frictional contributions from phase 1 and phase 2. When we consider the mixture equation, then naturally the interfacial shears, they cancel out, and this becomes a summation of the frictional contribution from phase 1 plus the frictional contribution from phase 2. Okay? So, this FW1 plus FW2, this has to be found out. After we discuss the conditions of choking and all those things, we will next concentrate on how to find out the frictional components in this particular case. This we had also to discuss when we were discussing the homogeneous flow model also. Okay. But in addition to homogeneous flow model, we find that there is one additional factor also which was not there in that particular case, and that is this particular del alpha del x, or in other words, if you expand rho Tp, it is alpha rho 2 plus 1 minus alpha rho 1. So, this alpha term is also not known here. For homogeneous flow, alpha was equal to beta, we could find it out. In this particular case, we do not know alpha. So, therefore, we need methods to calculate the frictional pressure gradient component of the total pressure gradient expression, and we also need some expressions to find out the void fraction. Okay. So, therefore, apart from whatever is there, apart from this particular equation, in order to find out pressure gradient, we need two additional equations, one for frictional pressure gradient and one for void fraction. And of course, apart from that, we also need relationships between the thermodynamic properties and so on and so forth. Okay. Now, we can derive these particular equations by analyzing each component separately. That we can definitely do, but usually the physics is not very well understood. And so, what we prefer when we do not understand the physics, we take a large number of data and we try to do some empirical correlations. Okay. So, here also, in order to find out void fraction and the frictional pressure gradient in terms of known input parameters, we would like to use some empirical correlations in the absence of any further information. This is what we would like to do. Okay. So, therefore, usually for finding out this alpha as well as the frictional component, we would like to derive the equations, or rather a common technique is to use the empirical correlations to predict the frictional pressure gradient as well as to predict the void fraction. And of course, certain simplifications come up. For example, when only one component is in contact with the wall, that happens for annular flow. Under that condition, we have just Fw1, there is no Fw2. So, such a simplification can also come. Sometimes what happens, we find that the drag force, it is a function of the relative velocity. So, depending upon the relative velocity, we can find out the drag force accordingly. Maybe the drag force is more important than the wall drag. So, depending upon the situation, we will be modifying it and we will be getting a much more simplified expression from this generalized expression, from which we can calculate the pressure gradient when two phases are in separated flow conditions. Okay. Depending upon the actual flow situation, certain terms will be cancelling out, certain terms will be remaining, and finally, you will get different final expressions in order to calculate the pressure gradient for the particular flow pattern you have in question. Okay. So, tomorrow we will be dealing with the conditions of choking, and after we finish that, we will be going for the different empirical approaches which are there for finding out the void fraction as well as the frictional pressure gradient. Thank you very much.